Hello everyone, welcome to lecture 7 of week 2. We have been reviewing the various methods for solving indeterminate structures, force method and displacement methods. In the last class, we discussed the basic concept behind force method, where the forces are essentially the primary unknown. And then when we say indeterminate structure, means the equations of equilibrium are not enough to solve the structure completely. So, we need additional equations, and in the force method additional equations are formed based on the compatibility condition. And what is the general procedure that we discussed in the last class? The method which is come under the category of force method is method of consistent deformation, and the different steps we discussed in the last class. Now, what we do today is based on a similar concept. There is an important equation called 3-moment equation, which is very useful for solving continuous beam. We will just quickly review the concept of 3-moment equation. Okay. You see, one important thing again I want to make here, and probably I will be repeating this thing next few lecture. The methods that we have learnt in structural analysis 1 and what we have been reviewing in the first 2 weeks, all the methods we really do not use them as it is today for analyzing real life structures. And that is not the purpose of these 2 weeks also. We are not going to demonstrate those methods through any examples. But the concept that constitute the basis of these methods, those concepts are important, because the similar concepts, the same concept will be used for formulating the more advanced structural analysis method, matrix method of structural analysis. So, here we will concentrate only on the concepts behind different methods, like force method we discussed, and the 3-moment equation we will discuss today, and then displacement method and various aspects of displacement method that will be discussed in the subsequent weeks. So, there will be no demonstration through any example. It is the basic concept which form the method. Okay. So, 3-moment equation, let us understand or review rather the 3-moment equation through an example. This is an example, this continuous beam which is statically indeterminate structure. We can easily compute the static indeterminacy of the structure. Here it is 2 reactions here. Here it is two reactions, one horizontal reactions, one vertical reaction. Here it is one, then another vertical reaction, another vertical reaction. So, total number of unknown the reactions are 6, and the number of equations total are unknown 6, and the number of equations available is 3. So, it is statically indeterminate structure. Okay. Now, you see what is 3-moment equation, as name suggests. This equation has moments. The equations are written in terms of moments, and every equation there are 3 moments constitute an equation. Now, you see, so let us write this. This is the entire structure. All the forces are expressed, all the reactions are expressed in terms of their equivalent reactions. Now, you see, if you remember in the force method, the first is first step. Once we calculate the number of static indeterminacy, then the next step, which is very important step, is to identify the redundant forces. Now, redundant forces could be anything, but at the end of the day, what is important is, once you choose the redundant forces and create the basic or primary structure, the basic determinate structure, your structure should be stable. Okay, determinate and stable. We demonstrated, or rather the examples that we, not the example, the concept that we used, concept was demonstrated by taking reaction as the as the redundant force, but not necessarily that we always have to take the reaction as the or vertical reaction as the redundant force. For instance, in 3 moment equation, instead of the force the reactions B y, C y, E y, it is the moment at various joints are taken as redundant. Now, once you take the, so you have, so we have in this structure the static indeterminacy is 3. So, redundant forces has to be 3. So, let us take the moment M A, moment at A, moment at B and moment at C. Instead of taking A y, B y and C y are the redundant forces, let us take moment M A, moment at B and moment at C are the redundant redundants. Okay. Now, we can take moment M A, M B, M C are the redundant, because M A, M B, M C they are the continuous at the beam is continuous at A, B and C. Therefore, there is moment at A, B and C. Now, the next step is, once you choose the redundant force, next step is we have to release that corresponding constraint. Now, had it been A y, if we choose A y as the redundant force, then we have to release these constraints. So, this support needs to be released. Therefore, the deformation in that particular direction is allowed. So, if you take B y as the redundant, so this support needs to be released, and therefore, the vertical deformation, the transverse displacement in direction B will be allowed. But now, since moments are taken as redundant, so the associated displacement or associated kinematic variable for the moments is the rotation. Okay. So, since moment at A, moment at B and moment at C are the redundant, therefore, corresponding kinematic variable is the rotation which needs to be released, and therefore, rotation at A, rotation at B and rotation at C will be now allowed. There is no constraint against rotation at B, rotation at C and rotation at A. It means that we provide now instead of the continuous beam, now we provide some internal hinge at point A, B and C. Right? If you recall that was the first step we do in while deriving the equation for 3 moments. So, once we insert an internal hinge at A, B and C, then automatically there is no constraint against rotation at point A, B and C, therefore, and which is same as releasing the moments M A, M B and N C. Okay. Now, so therefore, these are the internal hinges, these are all internal hinges, this is internal hinge, internal hinge, internal hinge. Okay. So, the redundants are now the moment M A, M B and M C. Okay. Now, let us see, once we have taken moment M A, M B, M C, and let us consider only this part. Let us consider only this part. Okay. And so, because these parts includes the moment at A, moment at B and moment at C, and 3 moment equation is essentially an equation which tells us how the moment at A, moment at B and moment at C are related to each other. Okay. Let us take L A B, L I A B, E A B are the length of A B, second moment of area of cross section at A B, and the Young's modulus of A B. Similarly, L B C, I B C and E B C are the length, second moment of area and Young's modulus of B C. Okay. Now, once we have identified the redundant forces and release the corresponding force by allowing the corresponding associated displacement. Now, the next step is to make the structure or create the basic determinate structure. Okay. The basic determinate structure now here is, if we consider this part, this is the basic determinate structure, right. Now, the basic determinate structure which is subjected to the external load. Now, suppose under the action of this external load, this is the deflection, and now by looking at the deflection pattern, you can easily make that the deformed shape is continuous at B, but it is not differentiable at point B. The slope is not continuous at point B. Okay. Because the rotation at this point, rotation of segment A B and rotation of segment B C, they could be different. Okay. Now, So, suppose theta B A is the rotation at B in segment B A, and theta B C is the rotation at B at segment B C, and then this is the basic determinate structure subjected to the subjected to external load, and then we also need the basic determinate structure subjected to the redundant forces. The redundant forces are the moments here. So, this is the basic determinate structure subjected to redundant force, and then the linear superposition theory says our actual structure, the solution of the actual structure should be equal to the solution of these two. So, this plus this, that is what we did in method of consistent deformation. Okay. So, compatibility between this deformation and between this deformation needs to be maintained, and that compatibility gives us the additional equation. Now, so deformed shape of this is, suppose this, and theta bar represent the rotation at B for the redundant, due to the redundant force. Okay. Now, so we can solve this using any method. Let us do it using the moment area method. Moment area method, first we have to calculate the bending moment diagram. Suppose this is the bending moment diagram for AB, and this is the bending moment diagram for BC. Again, look at the bending moment, it should be consistent with the problem. The moment at B is 0 in this case, because rotation is not constrained here, rotation at B is allowed. So, moment will be 0 here. Now, similarly, the bending moment for this is this, where M A, M B, M C are the moments at B, moments at A, B and C. Okay. Now, we need to recall one important theory, the moment area method. The moment area method, there are two theorems of moment area method. Theorem 1 says that how to compute the slope at a given point, and the theorem 2 tells you how to calculate the deflection at a given point. The theorem 2 is which is important in this case. It says that if you have a deformed shape, it is an elastic curve. If it is an elastic curve, and if you take 2 points in an elastic curve, say point A and B, and the bending moment between M is the bending moment and EI is the flexural rigidity, and the MI EI diagram between 2 points is this, then the and if you have a slope at point A is this and slope at point B is this, and the angle between these two slope is theta AB, then the theorem 1 says that theta AB will be the area of this bending moment MI M by EI diagram, and theorem 2 says that the deviation of point B, this is point B and its deviation is this is the deviation of point B with respect to the slope at point A. So, this is the slope at point A, and the deviation of point B is the projection of point B on to slope at point A. See, this deviation is given by the moment of this M by EI diagram about point A. That is the moment area theorem. If you can recall. So, same theorem can be used here. So, if we use, suppose AB is the moment, the area of this diagram, and ABC is the area of this diagram. So, then what we can take is, so this is the deflection at this is the deviation of point A with respect to slope at B, similarly deviation of point C with respect to slope at B, and similarly we can have deviation of point A and B with respect to slope at B in this case. So, these values, these we can obtain, these we can obtain from this diagram, and this and this can be this and this can be obtained from these two diagram, right. Now, then if we do that, then this is the, suppose x A B x C B are the centroid, distance of centroid from A and C, and then delta B A is equal to this is the moment M by EI diagram, this is the area of the moment, and this is MI EI diagram, M by EI diagram, and this is the centroid of that diagram. So, similarly, once we have delta B A, now once we know this value, if this is known, this angle can be obtained as delta B A by this length, which is LAB. So, theta B A is equal to this. Similarly, we can have delta C B and theta B C is equal to this. for the second case, second diagram, second basic indeterminate structure subjected to the redundant force, we can do the same exercise, and if we do that, then theta B A bar means the angle at B A, rotation at B A in segment, rotation at B in segment B A can be obtained like this, and similarly rotation at B in segment B C can also be obtained like this. So, once we have all the rotations, the determinate structure, the primary structure, the basic determinate structure subjected to external load, and the basic determinate structure subjected to redundant force. Once we have the deformation in both the cases, the next step is to calculate, apply how these deformation should be related to each other, so that the compatibility in the actual structure is satisfied, right. Now, these are the theta B and theta B C. Now, let us, what is the compatibility in this case? You see, the compatibility condition will be, suppose if we take any continuous beam, suppose it is A, this is say B and this is C, and suppose deform shape in this structure, deform shape is suppose something like this. Something like this. Okay. Now, what is important here is and the slope is like this, slope is like this. What is the compatibility at B is if this is theta 1, this is theta B A, and this is theta B C. The compatibility condition says that theta B A should be equal to minus theta B C. Okay. So, this angle should be equal to this angle, the minus because the way you measure this angle clockwise anti-clockwise. Now, if we have this, the compatibility condition will be at point B will be, so total angle, total rotation at point B will be, this is the rotation due to the basic rotation in the basic determinate structure due to external load, basic determinate structure due to redundant force, basic determinate structure external load, basic determinate structure redundant force. So, this is the total rotation in B A at B in segment B A, and this is the total rotation in B C. So, this should be equal to minus of this, that is the compatibility condition, and if we substitute the corresponding values, then we have this equation. So, this is called 3 moment equation. The reason is this is called 3 moment equation. You see, this equation actually relates moment M A and then moment M C and then moment M B. And other than these 3 moments M A, M B and M C, all other parameters, you look at this equation, all other parameters are known. So, only unknown in this equation is M A, M B and M C. Now, so this is essentially what? This is essentially the compatibility equation only. This is a consistent deformation. The basic concept of force method is same thing here, but the equation is written in terms of moment. Okay. Now, similar equations you can have now. We can apply this 3 moment equation for point A, point B, point C. Every time we have a set of equations and then solve all these equations to get the unknown. Okay. So, this is the concept of 3 moment equation, if you remember. Now, this is 3 moment equation. Now, another important addition in or important part in 3 moment equation is the support settlement. You see, suppose in a continuous beam, if any support settles means if there is a displacement in the support, that could be because of anything, because of the construction problem, because of the sinking of the structure, because of the settlement of the soil, it could be anything. But in any case, if there is a settlement of the support, then that settlement will cause moment in the structure. So, 3 moment equation allows you to consider settlement of the settlement of the support. So, the same equation that we derived here, we can extend it further, we can modify it in order to account for that support settlement. Suppose consider in this case the support B, which was originally at this point, now it settles like this, and the now position is B dash, and then suppose delta B is the settlement of the settlement of support B. Now, if the settlement of support B, I mean just to look at this could be the deformed shape, the red one is the deformed shape. You can see that in the deformed shape the support B is also is coming down, it is being so, because of the settlement of the support, the moment that is caused, that also need to be accounted for. Okay. Now, next is take a very general expression. Again we consider the same same segment A B and B C. Support delta B is the settlement at the support B, delta and delta C are the settlement at support A and C respectively. This is a general equation. If we see that there is settlement only in support B, there is no settlement in support A and C. So, we can make delta and delta C 0 in the expression. Okay. But the expression that you derived is for general. Now, once we so additional rotation, because of the settlement of the support, the additional rotation takes place at point B, and that additional rotation, suppose delta B delta BA is the relative displacement in segment BA, and delta BC will be the relative displacement in segment BC. Once we have the relative displacement and the lengths we know, then we can calculate the additional rotation at point B because of the relative displacement in AB is equal to this, and similarly the additional rotation at B due to the relative displacement in segment BC is this. So, this and this, then the total displacement will be, or the total rotation will be the rotation that we already calculated, two rotations, basic determinant structure under the external load, basic determinant structure under the redundant force, and then the third component in this case will be the rotation due to the support settlement. Okay. So, if we have this, then there are three components. This is the component of primary structure, our basic determinant structure subjected to external load, basic determinant structure subjected to the redundant force, and then the basic determinant structure, primary structure that is the subjected to the support settlement. Now, once we have that, once we have all the components, then we have to apply the compatibility condition. Okay. Now, compatibility condition, but please note one point here, all these theta BA, theta C that we obtained based on the methods that we studied for determinate structure, right. Now, then compatibility equation condition at B will be what? Compatibility condition will be at B will be, this is again this total rotation at B in segment BA, and then total rotation at B in segment BC. And if we add them, now next is we have to substitute all these variables from this expression, and if we substitute that, then what we have is this is the expression for the general expression for three moment equation when there is a support settlement. Or now, if there is no support settlement, say this part can be 0. So, the expression becomes the same expression that we just now derived. Okay. Now, slightly simplify this equation. Simplifying this equation is, you see, if Young's model EI is constant, means the flexural rigidity of the entire beam is constant, then from the previous expression these EI may get cancelled, these all EI, if they are same, then this may get cancelled, and if we do that, then what we have is, this is the expression. This is the expression what we have. Now, in addition to that, if EI are constant, but there is no support settlement, then this can be made 0, this part can be made 0, this part can be made 0, and the equation becomes this. So, in this expression you see, only thing is MA, MB and MC are the unknown. So, this equation gives you how these three moments are related to each other. Moments at three consecutive supports are related to each other, and then we write this equation at every point and get the system of equation, and in that system and then solve it. Just to quickly demonstrate that, we can tell you with this same example. If we take the same example, here you see. So, okay, we can take the previous one, we can go back. Yes, now we have the relation between MA, MB and MC. Now, we have relation between MA, MB and MC, right. Now, MA, MB, MC are means we have a relation between three moments in three consecutive support. If we are considering the compatibility condition at B, then we have relation between MA, MB and MC. But if we compute the compatibility equation at A, then we have a relation between MD, MA and MB. That is for compatibility equation at A. If we consider compatibility equation at B, then we have a relation between MA, then MB and MC. Similarly, if we consider the compatibility equation at C, then we have a relation between MB, MC and MA. So, ME. So, essentially we have three equations, the equation 1, equation 2 and equation 3. And three equations we obtain by satisfying compatibility equation at A, B and C, right. But these compatibility equations are written in terms of moments. Okay. Now, you see, since this support is a hinge support, so automatically MD become 0, and this is a roller support, so automatically ME becomes 0. So, in these three equations only unknown we have MA, MB and MC. Three equations, three unknown, we can solve for MA, MB and MC. Once we solve for MA and MB, once MA, MB, MC are known, then rest of the things can be obtained easily. Okay. So, what we do now is we stop here today. So, this is again we discussed the concept of force method today. It is based on the concept of force method or method of consistent deformation, the 3 moment equation, and next class we will review the concept of displacement method and then see how the displacement method can be taken further to formulate, again the same thing I am repeating, how the displacement method can be taken further with the knowledge that we learned in structural analysis 1, how the displacement method can be taken further to form a very general analysis procedure. Okay. Thank you. See you in the next class.